Okay, right. So I think it's now safe to continue reading on the topic of mechanism of breakdown of gases. Okay. This ionization by radiation or photons involves. Okay, we have to. This is deep reading. Okay, so we need to read with understanding. This ionization by radiation, meaning ionization is happening because of subjection to radiation. So it's almost like because there's radiation, and through that process of radiation, meaning you are exposed to radiation, and that process of being exposed to radiation, in that we now have ionization happening, simply meaning whatever was, in this case, let's assume not charged, it is now charged. And why is it charged? Because it has been subjected to radiation. Or photons involves the interaction of radiation with matter. Okay, there's that perspective also. And now we can talk about photoionization, which occurs when the amount of radiation energy absorbed by an atom or molecule exceeds its ionization energy and is represented as A plus HV. And this leads us to saying A plus plus E, where A represents a neutral atom. Oh, yeah, a neutral atom or a neutral molecule in the gas, and HV, the photon energy. Okay, all right, let's do this. So over here now, we are talking about photoionization, and we are saying that it happens when the amount of radiation energy, absorbed by an atom or a molecule exceeds the ionization energy and is represented as A plus HV, leading to A plus plus E. E in this case, let's assume it's an electron, where A represents a neutral atom or a molecule in the gas, and HV is the, so simply meaning, what do we have? Remember, it says A represents a neutral atom. Here's A. It represents a neutral atom. Here's A charged or A ionized. Simply meaning our neutral atom, it is now ionized. Okay, so essentially what's happening here is, here you have a neutral atom or a molecule in the gas, né? And what is HV? HV, it's the photon energy. So when you say photon energy, you add that up with your neutral atom, né, or molecule in the gas. Okay, then what do you end up with? You end up with A charged, where it's now no longer neutral, it's now charged, plus E. Okay, now let's continue reading. Photoionization is a secondary ionization process and is essential in the streamer breakdown mechanism and in some corona discharges. So there's a type of discharge, we refer to it as the corona discharge, and it says photoionization, simply meaning the charging process. How do you get charged? You get charged by being exposed to photon energy. So simply meaning you have a neutral particle, you subject it to what we call photon energy, okay, and that process leads to photoionization. And this photoionization, it is a secondary ionization process and is essential in the streamer breakdown mechanism. So simply meaning there's another breakdown mechanism referred to as the streamer breakdown mechanism. Okay, and this mechanism, as well as in some corona discharges. Okay, so there's a link there, there's a relationship there. Yeah? So now we say if the photon energy is less than, what is the photon energy? The photon energy, it is what? HV. So if HV is less than the ionization energy, where does this ionization energy comes from? Let's assume that this ionization energy, it comes from an external source. Okay, so here it says if the photon energy is less than the ionization energy from the external source, it may still be absorbed, thus raising the atom to a higher energy level. So even if it is less, it will still be absorbed, and it will now raise the atom to a higher energy level. And this is what is known as photoexcitation. Wow. So I'm hoping that you are making a note of that somewhere. Okay, right. The lifetime of certain elements in some of the excited electronic states extends to seconds. The lifetime of certain elements in some of the excited electronic states. So there's this excited electronic state. It's a state where you reach that state if you are excited electronically speaking. And then the lifetime of this happening, it basically extends to seconds. These are known as metastable states. And these atoms are known as metastables. Okay, metastables have a relatively high potential energy and are therefore able to ionize neutral particles. Okay, let A be the atom to be ionized in B to the power of M. Let that be the metastable, where the metastable collides with our atom to be ionized with A. Okay, and that ionization may take place according to the reaction, and this here is the reaction. Okay, ionization by metastables. Now what is a metastable? It says here B is the metastable. So ionization by metastable interactions comes into operation long after excitation, and it has been shown that these reactions are responsible for long time lags observed in some gases. So if you want to refer to a time lag that is long in some gases, it's because of ionization by metastable interaction that now come into operation long after excitation, and it has been shown that these reactions are responsible for long time lags observed in some gases. Thermal ionization, now there's something else. Now we are talking about what? Thermal ionization. The term thermal ionization in general applies to the ionizing actions of molecular collisions, radiation and electron collisions occurring in gases at high temperature. When a gas is heated to high temperature, some of the gas molecules, they acquire high kinetic energy, and these particles, after their collision with neutral particles, ionize, meaning they become charged. They ionize them, and then they release electrons. These electrons and other high velocity molecules in turn collide with other particles and release more electrons. Thus, the gas gets ionized. In this process, some of the electrons may recombine with positive ions, resulting in neutral molecules. Therefore, a situation is reached when under thermodynamic equilibrium condition, the rate of new ion formation must be equal to the rate of recombination. Using this assumption, Saha derived an expression for the degree of ionization, in this case beta, in terms of the gas pressure and absolute temperature as follows. We will look at this at a later stage, just not now, so let's skip it. Okay, where P is the pressure in torr. Okay, so P is the pressure in torr. Okay, then also W subscript I, okay, which is the ionization energy of the gas, and then K is the Boltzmann's constant. Okay, and then beta, it is the ratio N subscript I divided by N, and N subscript I is the number of ionized particles of total N particles. Since beta depends upon the temperature, it is clear that the degree of ionization is negligible at room temperature. Also, if we substitute the values of P, W subscript I, which is our ionization energy of the gas, K, which is our Boltzmann constant, as well as T. Now, what is T? For now, let's assume that T is some type of temperature, okay? It can be shown that thermal ionization of gas becomes significant only if the temperature exceeds 10,000 kelvins. It's 1, 2, 3, so that's what, 1,000 kelvins. Yeah, it's 1,000 kelvins. Okay, so we'll stop there for now.